we were in the middle of solving the Monge-Ampere equation. Just to remind you of the setup. So there's our domain. Ck plus 2 alpha functions, so that the associated 1-1 form is positive definite, and so normalized by modding out by the constants, requiring mean value 0. Then the range is going to be space of f Ck alpha functions, such that the integral of e to the f minus 1 omega to the n is 0. And with the Monge-Ampere operator, m maps x to y. And that's given by m of u log this determinant, this ratio of volume forms. And the equation we wanted to solve is it's a one-parameter family of equations, so m of u sub t equals f sub t, where f sub t is given. So t ranges from 0 to 1. F sub t was log t times e to the f plus 1 minus t times a constant function 1, if you want. So at time 1, that's the equation that's going to give us Ricci flat Kähler metrics. At time 0, it's a trivial equation, and we want to interpolate between the two cases, from the trivial to the non-trivial case. I'll just summarize what we said last time, what is left to show here. So we needed to show that, one sort of neat way of phrasing what we need to show is that, so if we define the set capital T, that's all time intervals, all time points in 0, 1 for which a solution exists. We need to show three things: that T is non-empty, formally, but that's how we rigged it up. It's 0 belongs to that interval, so that's kind of clear. B, that T is open, and again that was sort of clear from the fact that the solutions are a priori unique. If there is a solution, then there is exactly one. So it's sort of by degree argument, like a mod 2 degree argument, if you had an even number of solutions, they could cancel out in pairs, and then you could just stop being able to solve at some given time. But since you a priori only have, at most one solution, you have to be able to keep solving at least for a little time. So this is the openness, so it's almost clear. But the rigorous argument is from the implicit function theorem, and I'm going to do that today. So it's very quick, actually. It's pretty easy. And then the hard part really is to show that T is closed. So that's somehow the statement that if you have a path of solutions, that path can't just somehow diverge to infinity before it reaches the final point. So that's going to follow from these a priori estimates. So assuming you have a solution, you show that the norm, the Ck plus 2 alpha norm of that solution has to be bounded sort of independent of T. So this means it can't just disappear. Okay, so the openness B that's pretty easy. So what's the picture here? So you have so if you Banach space CK plus 2 alpha, it's the other Banach space that's CK alpha. In here you have this, this open set that corresponds to functions u, so that omega plus del bar u is positive definite. And you have a hypersurface that's given by prescribing mean value 0. So it's just a linear hyperplane. So this piece there is your x. An open subset of a hyperplane of a Banach space. And over here you have a hypersurface of a Banach space 2 given by this one equation, integral e to the f minus 1 equal to 0. There's some hypersurface here, so that's y. And what I claim is that, if I have this nonlinear map, and what I'm claiming is what's pretty plausible from the picture, that if I linearize that map, then that linearization is going to be an isomorphism of the tangent spaces to these two guys, and the implicit function theorem tells me that in a small neighborhood of each point, M is actually like a diffeomorphism onto its image, so I can keep solving for a little while at least. So need to calculate the derivative of M. So dm at u, so that's going to be a map from the tangent plane to x at u, to the tangent plane to y at m of u. That's pretty clear what this is, because this is this is an open set. X is an open set of a linear subspace, so the tangent plane is just going to be that linear subspace. So it's going to be all v in ck plus 2 alpha, so that the integral of v with respect to omega n is 0. So the tangent plane to y, well, that's what you get if you linearize that condition, integral e to the f minus 1 is equal to 1, so that's all functions g and ck alpha, so that the integral of g with respect to that weighted measure e to the f, omega to the n is equal to 0, where m of u equals f. And so this guy here, this e to the f times omega to the n, that's by construction just omega plus idd bar u to the n. So if the volume form associated with that modified Kähler form. And now only need to calculate the derivative of m actually, and that's going to be a linear differential operator, and the only thing that's around is a Laplacian really, so it's going to be Laplacian actually. It's not hard to see. So dm at u applied to v is, well, so you have to vary u in a one parameter family here and then differentiate by the family parameter. But this is like an nth power of a form, and it's a two form. So two form, like the algebra of two forms or generated by two forms is commutative. So you can just differentiate like you would differentiate the power of real numbers. So that's going to be, from the log, I'm going to get omega, like the inverse. And then n times omega plus idd bar u to the n minus 1 wedge idd bar of the tangent vector, so that's my function v, divided by, so that stays the same, omega to the n. So these guys cancel out, and that is just 1/2 times the Laplacian with respect to omega plus idd bar u of v. So it's again this thing that if you take any 1 form and wedge it together with the n minus first power of the Kähler form, so that you get a volume form, and then divide by the nth power of the Kähler form, what you're going to get is the trace of that initial 1 form with respect to the Kähler form. So it's a trace of the complex Hessian with respect to the Kähler form, which is the Laplacian. So that's linear algebra. So it's the Laplacian of that metric up to some factor n over 2. So linearization is a Laplacian, and that's, so I'll quote that as a fact that that's an isomorphism between these Banach spaces. Functions with mean value 0 on one side, functions with mean value 0 on the other side. It's a one-to-one map. It's actually an isomorphism of Banach spaces. And notice that I need the alpha here. So the Laplace, I could drop the alpha a priori, and the Laplacian would still be a bounded operator from ck plus 2 to ck, but it wouldn't admit a bounded inverse in general. So the Laplacian only has a bounded inverse, if I add this parameter, so if alpha is strictly between 0 and 1, if I work on Holder spaces. So that's the Schauder theory. And then the implicit function theorem tells me that M is actually a diffeomorphism. One-to-one map in a small neighborhood. Okay, so then we need to talk about closeness of these a priori estimates. And I had this little flow chart last time, and I want to go over that again a little bit more carefully. So there's four a priori estimates in this business. So assuming that U sub t exists, need to show that the following holds. So I have the C0 estimate. This is bounded by some constant independent of t. I have that the Laplacian is bounded in C0 independent of t. Need that the Hölder seminorm of the Laplacian is bounded independent of t, and I want that. Ultimately, what I really want, that the full ck plus 2 alpha norm is bounded independent of c. Okay. So what's the logic here? So the first 3 steps are where all the hard work lies. Once you have all of these, then sort of Schauder theorem and the same theorem that I used here for the Laplacian, which is telling me that Laplacian on compact manifold is invertible between ck plus 2 alpha and ck alpha. Actually tells me once I have this control on the Laplacian and this control on the C0 norm, I get control on the full C2 alpha Hölder norm. So this is going to tell me that. So it's again Schauder theory. I'm going to get that the full C2 alpha norm is uniformly bounded independent of time. Same Schauder's over there, and then it's a bootstrapping argument to say, so you use Schauder iteratively, make an induction. That's pretty easy. So I'm going to show you how this is done to actually bootstrap this information to the full regularity that you need. This is shorter again. So in particular, this loop here, this is just linear PDE theory, so you can take as a black box if you want to. There's nothing to do with the structure of the Monge-Ampere equation. So there's a little error here that you actually need 1 to prove 2. And now 1 and 2 together give you something that's a little bit more complicated to state, but I'll state that in a second. And once you have that, you can sort of turn on a standard machinery to give you a 3. So this is something that's called Evans-Krylov theory, the Evans-Krylov estimates. They're not really specific to the Monge-Ampere equation, so they apply much more generally to a much wider class of nonlinear second-order equations. So this is sort of a well-understood theory once you have 1 and 2. This is well understood how you do that. So what's star? So star consists of 2 points. The first point is sort of again, sort of purely linear argument that doesn't really have anything to do with the Monge-Ampere equation, which is saying that so first you use LP regularity for the Laplacian. So this is like Schauder theory, but in Sobolev spaces rather than Hilbert spaces. So this is telling you that the W2P norm of U, so 2 derivatives, 2 weak derivatives in LP. So that's a statement of LP regularity, that this is bounded by the LP norm of U and the LP norm of the Laplacian of U. This, LP regularity for the Laplacian. That this is bound. 1 and 2 together tell you that the L infinity norms of these guys are actually bounded. So in particular, the LP norms for every finite p. For a finite value of p, you have this sort of estimate. So you know that U sub t lies in W2p for every finite p. That's what the theory tells you. And then you use Sobolev embedding twice. So you know Sobolev and Mori embedding. And that's going to tell you that UT is actually bounded in C1 alpha for every alpha between 0 and 1. So this is bounded by 1 and 2. So Sobolev and Mori embedding. I'll tell you that U sub t is controlled in C1 alpha. That's the first thing, but sort of more importantly, almost more importantly, is, you know that these sort of intermediate norms are controlled, and what this is also telling us, so we know that the Laplacian is uniformly bounded. The Laplacian is like the sum of the eigenvalues of the Hessian. Now, from the Monge-Ampere equation, we also control the product of the eigenvalues of the Hessian. That's just saying it's prescribing the determinant of the Hessian. So the Monge-Ampere says that the product of the eigenvalues is fixed. 2 says that the sum of the eigenvalues is fixed. The eigenvalues are positive numbers, so this means the eigenvalues can't be too large or too small. They can't be too large because the sum is controlled, and if one of them was really small, then the product would go to 0, and that would contradict the Monge-Ampere equation. So what this was, 2 plus the Monge-Ampere equation actually tell us that have sort of uniform comparison, that my unknown metric is uniformly bounded above and below by my reference metric. And this means that the Monge-Ampere equation is actually uniformly elliptic, because the So if the eigenvalues of this form with respect to the reference form, these are precisely the eigenvalues of the principal symbol of the linearization of the Monge-Ampere equation. I mean, the linearization of the Monge-Ampere is a Laplacian with respect to this metric. So if you want the eigenvalues of the principal symbol are precisely the eigenvalues of this guy with respect to the background guy. And this is now telling us that they're uniformly bounded above and below, so meaning that the equation is uniformly elliptic. And that's sort of the key word here. And once you have uniform ellipticity, so the Evans-Krylov machine starts, and that's sort of well understood. Once you have a uniform control on that, this is what you need up here. So this is really telling you that what you need to get a complete control, except for this fairly elementary step here that goes from the first three to the fourth, what you need is 1 and 2, so it's the hard parts. And they're quite different in each. I mean, one is nicer to explain in a way. They're both hard, but one is nicer to explain. I'll try to explain both. So I'll do the last, so the easiest thing first to show you once, if you have 1, 2, and 3, how you go to 4. So that's, so what you want to do is you want to prove by induction that, so k is fixed, k is some large integer. And so you want to show that, that the CL plus 2 alpha norm of ut is bounded by a constant that will depend on L for all L between 0 and k. And L equals 0 is precisely what I wrote down here, what sort of follows immediately from 1, 2, and 3 using the Schauder estimate. That's the inductive hypothesis. So L equals 0. So this is 1, 2, 3 plus Schauder. And for the inductive step, you're only going to use Schauder. You're only going to use black box linear PDE theory, but you're not going to be referring back to any of the previous estimates. So that's how these bootstraps work. So to go from L to L plus 1. So what you want to do is you want to take your Monge-Ampere equation, you want to take your PDE and differentiate it in the space variables. And that way you're going to get a PDE for the derivatives of your solution, and that way you get additional estimates on the derivatives of your solution by checking that they satisfy PDE. But the good thing is that if I differentiate a nonlinear equation by some parameter, I'm going to end up with a linear equation. So I only need estimates for a linear equation. So one way of saying that would be to say, okay, I mean it's a local argument. Locally. I'm going to give you a slightly simplified version of the thing, and you take X to be a local holomorphic vector field. So something like d by dzj, like a coordinate vector field on some local patch. And now you want to differentiate the Monge-Ampere equation by that coordinate vector field. And the nice thing is, if I'm assuming that the vector field is holomorphic, then it basically just commutes with Mohr-Ampere equation more or less. It commutes for the del bar at least. So that's not, I mean, just to make it look nice. It's not really necessary. So then if you so you differentiate the Mohr-Ampere in direction x, and then what you're going to get is that the Laplacian, so it's the same linearization argument, so that 1/2 times the Laplacian with respect to my unknown metric applied to x of ut is equal to x of ft. So I'm going to get a linear equation for my first derivative here. And now this is how the bootstrap works. So by the inductive hypothesis, the coefficients of my operator, so if the coefficients of the metric, this is controlled in CL alpha. So I have a CL alpha bound on this guy, that's the inductive hypothesis. Certainly I have a CL alpha bound on this guy, just because L is less or equal than K. I mean, in the example we care about, F is actually C infinity function, so it certainly lies in every Hölder space. But, just formally you could say, we're working with CK plus 2 alpha and CK alpha, so FT lies in CK alpha, L is less than K, so I'm good here. And for this guy, also know something that's one derivative of u sub t. U sub t lies in CL plus 2 alpha by assumption. So this guy lies in CL plus 1 alpha with an estimate. I guess both of these are true by the inductive hypothesis. And this is that's actually more than I would need. I would just need that the coefficients are in CL alpha, that the solution is already in CL alpha, and that the right-hand side is in CL alpha. So it really only needs CL alpha, so in all three spots, but you've got CL plus 1 alpha, who cares? And then Schauder theory tells me that the solution to my PDE actually lies in CL plus 2 alpha with estimates. So coefficients are in CL, right-hand side is in CL, solution is even in CL plus 1, but CL would be enough, so Schauder theory tells me that. So Schauder theory again tells me that I have a bound on x of u sub t in CL plus 2 alpha, so that's bounded independent of t by something that only depends on L. And now this is one derivative of my solution. So my since I can do that for all directions, this is going to say that my solution actually lies in CL plus 3. CL, not T. That's exactly what I needed to go from L to L plus 1. So this is how this bootstrap works. So it's almost completely formal once you have the idea of differentiating your PDE by some, by some coordinate vector field. Okay. Right. So again, I want to do 1 and 2. I mean, 3. This is Evans Krylov machine that's sort of well established, but it's a pain to set up and to explain. It'll take probably at least 2 lectures to do that. It's pretty technical, but it's sort of general and widely applicable. So it's trustworthy. That's what I mean. Okay. So so make a couple remarks first. The first one is that by now there exist at least 3 different versions of proving 1, and they're completely different from each other. So I guess there's what Yao did originally with some simplifications by Jerry Kasdan. So that's based on Moser iteration. That's the proof I'm going to explain. So this is that's a very nice construction. That's easy to explain, and it's a good thing to know. Speaking of knowing how to hammer nails, I mean this is a powerful hammer. And there's a pretty elementary proof that I found in these lecture notes by Botsky that I put into the syllabus, that used the Alexandrov maximum principle. It's sort of something coming from convex geometry. And so if there's a third proof by Kolodjev, that's a celebrated result in complex analysis. So he uses capacity methods of potential theory in several complex variables. So completely different proofs, and they give different results if you look carefully, and that's of the interest in having these different proofs. What you need for Moser iteration is that f lies in n over 2 plus epsilon. So I'm assuming that f is a C infinity function, okay? But just for the sake of pushing these methods as far as you can, and having the most flexible theorem. So the first one works if f is an ln over, half the real dimension, so it's a complex dimension plus epsilon. So the version I'm going to give is not going to be the sharpest one, and I'm going to have to use an L infinity bound on f. But if you look carefully, it works with f in half the dimension plus epsilon. This proof here requires f in L2 plus epsilon. And this one requires f in L1 plus epsilon. And that's sort of needed for modern applications to algebraic geometry. And you can't go below, L1 is out. L1 is out even for the Laplacian. That would work even for the Laplacian. And I guess the second remark is that I'm not going to write that down, but you should really, I'm going to show you the Moser iteration method, and you should really try to apply that yourselves to other equations. Even the Laplace equation, Laplacian u equals fc, what you get, or the equation that I put on the homework sheet yesterday, this problem about Schrödinger operators. It's a nice problem. Just try it. It's really easy to use, and it gives very nice results very quickly. So that's it's a good thing to know. Okay, so how does this actually work? So if you apply it to a linear equation, it only gets easier, but you still get results that you wouldn't get otherwise so easily. So I'm going to use this DDC notation. That's more convenient now. So I have my Morge-Ampere equation. So this is e to the f times omega n. Now what I'm going to do is subtract omega to the n on both sides. So it's going to be like this integration by parts trick like yesterday. It's going to be but you have to be, yesterday I just used the binomial formula to expand this, and then the leading term canceled out. There's something slightly smarter you can do. And this is saying that, you have a difference of nth powers, so you can do like a geometric series. You have a different, this to the n minus that to the n. So you can take out the difference between the two, and then you have like this, this sum in between. So this is actually DDCU wedge omega to the n minus 1 plus omega to the n minus 2 wedge omega plus DDCU plus omega plus DDCU to the n minus 1. And that's a better thing to do than sort of the rearrangement I did yesterday, because these terms here are positive forms by assumption. So basically you've created a sum of positive terms, which wouldn't have been apparent from the thing I wrote down yesterday. So that's a beautiful structure. And actually we're gonna drop all of these terms. So these are positive terms. Will drop eventually. So we're only going to be working with this term. So this is where all the nonlinearity of the equation sits. But because of this nice structure, it comes with a sign. Okay. So now what? I'm going to do the thing that you always do if you have an elliptic equation. You multiply by some power of the solution and integrate by parts, or try to integrate by parts. And what I'm going to do is I'm going to multiply this by u times u to the p minus 2, where p is at least 2, and integrate by parts. So actually could take p greater than 1 here, any p greater than 1. So that's useful in some contexts to have that freedom, but not, for us it's not important. You have to work harder to justify the argument, but you could take any p greater than 1. Okay, so then what do you get? So you multiply this, you have the DDC there, you integrate by parts, so the D is going to hit this factor. And if D hits any of the other factors over there, it's just going to go away because those are closed forms. So the question is, what is D of this guy? So note D of u times mod u to the p minus 2. This is actually just what you would think it's p minus 1 times mod u to the p minus 2 du. I put the absolute values signs there in this funny way so that this would be literally true. So you can check with u and minus u wherever appropriate and see that the signs check out. The reason for, if p is at least 2, then this guy is, even though I have an absolute value here, then this guy is actually a C1 function. So the derivative goes, it's bounded or even goes to 0 at the 0 locus of the function. So, but p greater than 1 is all I really need. I could regularize, I could regularize the absolute value a little bit, and then I wouldn't even have to worry about taking p at least 2 here and the thing being C1 anyway. So we have this. Okay. So what this tells me then is that the integral of of u to the p minus 2 times du wedge dcu, wedge this whole rho omega to the n minus 1 plus omega to the n minus 2 wedge omega plus id ddcu, and so on. This guy here is equal to, guess, 1 over p minus 1 times, I have a minus sign from integrating by parts, integral 1 minus e to the f omega to the n. And now what you have to realize is that, this is a 1-1 form, and it's a positive 1-1 form. So the eigenvalues of this 1-1 form in a normal coordinate system are just the mod squares of the derivatives of u by the coordinate vectors. So this is a 1-1 form that if you diagonalize is going to have like the mod squares of the first derivatives in the coordinate directions of u on its diagonal. There's a positive 1-1 form. And then you have all the positive terms, these positive terms here. And now this is the stage at which you're going to drop all these other positive terms. You're only keeping sort of the reference term here. And then, wedging together with the n minus first power of the Kähler form, dividing by the top power of the Kähler form is going to trace this 1-1 form. The diagonal entries are sort of the derivative squares of u in the coordinate direction. So if I sum them all up, what I'm going to get is a norm square of the gradient, up to some factor 2 over n. So this is going to tell me that 2 over n times integral u to the p minus 2 times grad u squared omega to the n is less or equal than, this is where I'm dropping these terms, 1 over p minus 1 integral 1 minus e to the f omega n. I think I've missed something everywhere, so because I need to multiply both sides of the equation by u times u to the p minus 2. So if I got that on the right hand side. And now this is almost the same expression that you would get if you're trying to do this with a Laplacian over the linear equation, except for this little loss of 2 over n from the combinatorics. So we'll do one more thing with this. So I have this term here, u to the p minus 2 times grad u squared. I want to rewrite that as the gradient of some function squared. So I sort of want to pull in this factor into the gradient squared. So u to the p minus 2 times grad u squared is actually the same thing as 4 over p squared times grad of u to the p over 2 squared. What this gives me, then if I bring everything to the other side, is that integral grad u to the p over 2 squared omega to the n is less than p squared over, I guess, np squared over 2 times p minus 1 times the integral of 1 minus e to the f u to the p minus 2 omega to the n. So this is the basic inequality. Okay, so what does that buy us? So first of all, we can set p equal to 2 and see what we get. So then we get that that this is just grad u squared, this guy here, that this is less than, and now I'm going to do triangle inequality here, right? This is a constant, I'm just going to pull out the sup norm of f, or the sup norm of this guy. Just going to pull that out as a factor. So I mean, this is, if you're more careful about this here, you see that all that's really needed is of the n over 2 plus epsilon norm of f, but I'm just going to pull that out. So it's just going to be some constant times the L1 norm. And now here, you're going to use that u has mean value 0. So u is perpendicular to the constant, meaning that I have a spectral gap, I have a Poincare inequality. So this is by Poincare. This is greater or equal than 1 over c times the integral of u squared. So because the integral of u is perpendicular to the constants. And now we're all set because we have a higher power of u on the left-hand side than on the right-hand side. So if you want, you can use Hölder's inequality here to convert this into a constant times integral u squared to the 1/2. So you can divide through. I mean, so you have the integral u squared with a square root here, but without the square root there, meaning you can divide through by this guy, and you're going to see that the L2 norm of u is uniformly bounded. So that's going to be the base of an induction. Yes?
Exponent, you just replaced exponent with some constant.
Yeah, I made it, I did the triangle inequality. I said, okay, I want to bound this. So when p is 2, this term isn't there, so it's just this thing times u. And I want to bound the absolute value of the integral above. So I pull the absolute value signs inside. That gives me the absolute value of u here. And then I just say this is some bounded function. It's just the right-hand side of my equation. It's just some bounded function. I just pull that out by a constant, by the supremum. Yeah, so this tells me that the writing the subscript again, that the L2 norm is uniformly bounded independent of t. You see that There's something else you see. So if you go back to the original inequality here, if f is identically 0, then this tells you that u has to be a constant, and because u is orthogonal to the constant, you actually get that u has to be 0. This is the uniqueness of solutions. So that you get the uniqueness of solutions as a special case of this argument. So if I call this star, then so if the remark here is that star for p equals 2, and so for the case f equals 0, implies uniqueness of solutions. Okay, so that's the base of an induction. And I'm going to say, well, I have the L2 norm under control. I want to go from the L2 norm to some slightly higher LP norm to an even higher LP norm, and then inductively going to get the L infinity norm in the limit, so the sup norm. So we're going to use that the sup norm can be written as the limit of the LP norms as p goes to infinity. To go from LP, to be precise, to L n over n minus 1 times p. So you look at star again, and now you use the Sobolev inequality. On M applied to the function u to the p over 2. So the Sobolev inequality is usually phrased by, so in terms of the real dimension, so that's 2n. So this is saying that the integral of u to the p over 2 to the 2m over m minus 2 to the m minus 2 over m that this is less than a constant, the Sobolev constant, times the integral of grad u to the p over 2 squared plus another constant times the L2 norm of the function that I'm applying the Sobolev inequality to, which is u to the p over 2 in this case, so times 2. You see, this is exactly the expression I've manufactured on the left-hand side of that inequality. So combine this with star. Well, maybe I'm gonna write this out again, but I'm gonna simplify the exponent. So this is the integral. So m is 2n, so I have n. Okay, so it's u to the n over n minus 1 p to the n minus 1 over n is less than a constant times, I've got np squared over 2 times p minus 1. But p is at least 2. So this is basically like p squared over p, so it's basically like p. So this factor there, this is important, how this depends on p. C times p, pull the subnorm of f out, times integral u to the p minus 1, plus what I get from the Sobolev inequality here, plus another constant times the integral of u to the p. And now I'm taking square roots pth roots everywhere. Up to some constant, that's certainly fine. So I can pull the sum out. This is not telling me that the L n over n minus 1 p norm of u is bounded by this is slightly nasty. So we have this guy here, times the max of 1 and the LP norm of u. So I have the LP norm of u here for sure. So that's not a surprise. Where does the max 1 come from? This is because I have like a p minus 1 here. And p minus 1 is better than p in this business because it's smaller than p. So I'm making a bigger inductive step, but because I have a p here, I sort of want to convert this into p2. So I can use Hölder's inequality here to bound that above by a power of the LP norm. But that power is going to be small. There's going to be an exponent that's smaller than 1. So if the LP norm is bigger than 1, then this is just bounded above by the LP norm. If the LP norm happens to be smaller than 1, then I just bound this by 1. But the bad case is when the LP norm is large. So this is just cosmetics here. And then so you're going to induct, you're going to go from, so P starts at 2, then it goes to n over n minus 1 times 2. Goes to 2 times n over n minus 1 squared, and so on and so forth. But you have to keep track of this constant here because that, a priori that blows up as p goes to infinity, so you have to keep track of that carefully. And then what you're going to get as the upshot is that the C0 norm of u, which is the same thing as the L infinity norm of u, which is the limit as p goes to infinity of the LP norms of u. That this is bounded by your constant to the 1/2. I'm going to need notation, so I'm writing gamma is n minus 1 over n. That's less than 1. So that's the inverse of this exponent that I'm improving by. So this is going to, if you work it out, it's going to be 1 plus gamma squared, and so on. So you're going to get a geometric series in the exponent here. And then you're going to get something like 2 to the 1/2 times, 1 plus gamma plus 2 gamma squared plus 3 gamma cubed plus 4 gamma to the 4. and so on, times the L2 norm of U. Right, you have this constant to the 1 over p, that's going to give you the first term if you iterate up. And you have the p to the 1 over p, and if p runs over this sequence, then this is going to give you this 1 plus gamma plus 2 gamma squared plus 3 gamma cubed, which is, slightly worse than a geometric series, but it still converges because gamma is less than 1. So this tells you that we know that this guy is bounded, so therefore the C0 norm is bounded. So that's the Moser iteration. So my time is up. If you want to know about the proof of this other estimate, the second estimate, just ask me. I'm happy to tell you. Otherwise, that's it. Okay.